Alright, so today we're starting with carboxylic acids and acid derivatives. Okay. So this is actually organic acids and derivatives. Right, it's got derivatives, for example, an example of a carboxylic acid derivative is an acyl chloride, right, where a chlorine atom substitutes the OH. So that's a carboxylic acid derivative. Okay. So first we're just going to look at some common carboxylic acids that we should all be familiar with, right? We have methanoic acid, ethanoic acid, right? These are just some of the carboxylic acids that we're familiar with. Propanoic acid, right? We also have ethane dioic acid, something we've seen before, right? Make sure it's shown bonded to the oxygen. And then we have benzoic acid. So these are just some examples of carboxylic acids that we're familiar with. Okay. So here you have methanoic acid, ethanoic acid, okay, propanoic acid, and so on. And then this is ethane dioic acid. इसका नाम sometimes you'll see it come up as ethane 1,2 dioic acid, but again, numbering isn't necessary, right? It's redundant in this case. You know कि carbons 1 and 2 पे ही होंगी वो acids, right? And then you have benzoic acid. So when we talk about carboxylic acids, we know that carboxylic acids are weak acids. So generally we can write a carboxylic acid like this, right? It says RCO2H, right? RCO2H. And when it reacts with water, right, we can say that, or in aqueous solution, we know that it partially ionizes, right? It partially ionizes in solution. Right? I mean, this equation can be simplified as the following. You have an acid that's ionizing to form the conjugate base and H+. So that's the ionization of a carboxylic acid in water. Now the question we want to answer is why are carboxylic acids weak acids, or why do they behave as acids? Right? Why does the carboxyl group ionize in solution? Let's say if you were to compare it to something like, say, an alcohol. So let's say we have an acid group here, okay, versus an alcohol, okay, and versus a phenol even, let's say, okay. Now we know that phenols are acidic, so we know phenols are acidic, but carboxylic acids are actually more acidic. Carboxylic acids are actually more acidic, okay, and alcohols are obviously non-acidic. Now why is that the case? The reason why carboxylic acids are more acidic, okay, are more acidic than phenol and alcohols, okay, because of the electron withdrawing effect, again, electron withdrawing effect is known as negative induction. Okay? The electron withdrawing effect of the oxygen atom, okay, in the C double bond O weakens, okay, the OH bond. Okay, so the electron density is withdrawn from the OH bond towards the C double bond O. So therefore you have a weaker OH bond. Okay, therefore it's easier, making it easier for H plus to form. In other words, making it easier for the acid to ionize. Okay, but a better explanation for this is in terms of the conjugate base. Okay. Now, if you guys remember in the last class, I showed you guys this over here. Okay, or a few classes. If you guys look at the conjugate base of the carboxylic acid, okay, we have this guy over here, right? This can also be represented as this over here. These are called resonance structures. Again, as I mentioned, you don't need to draw resonance structures. The purpose of drawing a resonance structure is these two different structures are equally as likely when this dissociates. Okay, the negative charge could be on this oxygen or on this oxygen. Now, asli mein kya hota hai? The negative charge isn't actually localized on either oxygen. These resonance structures essentially are an illustration to represent this idea that in actual fact, जो आपका negative charge होता है, it's actually distributed evenly between the two oxygen atoms. It's distributed evenly within the two oxygen atoms. So it doesn't actually lie on one of the oxygens or the other. It essentially lies over the two oxygen atoms. So you have a highly delocalized negative charge. In other words, it's not very dense. So if the charge density is much lower, it means that it doesn't combine with H plus very easily. So it remains dissociated. The backward reaction doesn't occur readily. Because the charge density on this guy is very low, it doesn't combine with H plus very readily, so the backward reaction isn't very favored relative to, let's say, phenols. Phenols mein the resonance isn't as strong as it is in phenol ke jo conjugate base hai, phenoxide ion, usme the resonance isn't as prevalent as it is in this one, okay, which is the conjugate base of the carboxylic acid. So over here we can say that there is delocalization, okay, delocalization of the negative charge, okay, over the two oxygen atoms, okay, in the conjugate base, okay, makes the conjugate base more stable. So in other words, if it makes the conjugate base more stable, it makes it less reactive towards H plus and favors ionization. Okay. And again, delocalization means that there is a decrease in charge density. Delocalization implies a decrease in charge density. Alright, now let's compare the relative acidities. Let's compare the relative acidities of, say, you have methanoic acid, okay, you have methanoic acid here, and you have ethanoic acid. Which of these is the stronger acid? So here you have an alkyl group. You have an alkyl group over here that has an electron donating effect, right? It has an inductive effect. So let me rewrite this like this. If you have ethanoic acid here, right, the methyl group over here has an electron donating effect, right? Which means that what you're doing is if you compare the conjugate bases, so here you have HCO2 minus, and here you have CH3CO2 minus, right? What you have is you're essentially making the conjugate base more reactive or less stable. So it doesn't want to remain ionized as much. This one wants to remain ionized more. It's less reactive towards the H plus. This is more reactive towards the H plus. So we can say that over here, methanoic acid is a stronger acid than ethanoic acid. Okay. Methanoic acid is more acidic than ethanoic acid. Okay. And the reason why is that the electron donating effect, or again the positive inductive effect, okay, of the methyl group of the methyl group makes the ethanoate ion less stable than the methanoate ion. We're comparing the conjugate bases. Ethanoate ion less stable than the methanoate ion. Okay? And again, the more stable the conjugate base, the stronger the acid. Now let's take the same acids over here, right? But now let's also compare this with benzoic acid. Now, which of these do you think is the strongest acid? So over here, okay, methanoic acid is still the strongest acid, but benzoic acid is actually stronger than ethanoic acid. Okay, and the reason why is because of this. Now, if you think of methanoic acid is the simplest acid, obviously. So there's no inductive effect, no resonance, nothing, except for the C double bond O, which resonance है normally. उसके अलावा कोई additional resonance किसी भी चीज़ की वजह से नहीं. अब CH3CO2H में we just saw that we have this resonance, we have this inductive effect, electron donating effect of the alkyl group. Now in benzoic acid, you do have the same inductive effect, and you have 6 carbons here versus 1 carbon. So you might say, you know what, this will be weaker than ethanoic acid, but there is also, to a much smaller degree, there is also resonance effects. Benzene ring के साथ delocalization of electrons. जिस तरह से फिनॉल में हमने देखी थी ना ऑक्सीजन एटम की delocalization of electrons, इसी तरह से इसमें भी delocalization of electrons होती है. We don't really study in detail how it happens like we did for phenol, okay, but you should know that there is a little bit of resonance due to the delocalization of electrons due to the presence of the benzene ring. It doesn't overcome the inductive effect entirely, but it slightly overcomes it, meaning that benzoic acid is still a stronger acid than other carboxylic acids with alkyl groups. So like ethanoic, propanoic से ज़्यादा acidic होगी, but like methanoic से फिर भी कम होगी. So the inductive effect is only slightly overcome by delocalization of electrons. The delocalization isn't as strong as you had in phenol, because the oxygen atom isn't directly bonded to the benzene ring, but there is still some delocalization. Okay, and so the evidence for this, if you guys wanna, is the pKa, right? The pKa for this guy over here is 3.75. Methanoic acid for benzoic acid is 4.2, and for this is 4.76. Again, you don't have to memorize these values, but remember, the larger the pKa, the smaller the Ka, or the smaller the pKa, the larger the Ka, the stronger the acid. So जितना छोटा pKa होगा, उतनी strong acid होगी. Okay. All right. Now next, let's compare these groups over here. Okay. So now we've seen this. Now let's compare something like ethanoic acid. Okay. Let's compare something like ethanoic acid with something like chloroethanoic acid. Chloroethanoic acid means you have a chlorine atom bonded to the alkyl group over here, right? Now, which of these is more acidic? Chlorine is an electronegative atom, so it withdraws electron density away from the carboxyl group. So therefore, chloroethanoic acid is a stronger acid than ethanoic acid. Okay. So over here we can say that ethanoic acid, okay, ethanoic acid is less acidic, or we can say that chloroethanoic acid is more acidic. Okay. Chloroethanoic acid is more acidic than ethanoic acid. Okay. And the reason why is because the chloroethanoate ion, right, that's the conjugate base, right, that's the conjugate base, the chloroethanoate ion is more stable than the ethanoate ion due to the electron withdrawing effect of the chlorine atoms. Okay. Again, the electron withdrawing effect is also known as negative induction. I'll write this down. Okay. The pKa for ethanoic acid is 4.76. The pKa for chloroethanoic acid is 2.87. So there's a difference of almost 2, which means it's 100 times more acidic. So it's a logarithmic scale, right? So that's 2 का फर्क अगर है इसका मतलब 10 to the power of 2 का ionization में फर्क है. Okay, it ionizes 100 times more than this. All right. Right. So if you were to compare these three over here, now let's say that we have, I'm not showing the CH bonds, but let's say that we have chloroethanoic acid, then you have dichloroethanoic acid, then you have trichloroethanoic acid, right? Which of these will be the strongest acid? Trichloroethanoic acid, right? As you increase the number of chlorine atoms, what you're doing is over here, you're basically withdrawing more and more electron density away from the carboxyl group. Okay? The more electron density you withdraw, right? If you think about the conjugate base, the lesser your negative charge on the conjugate base, on the CO2 minus, right? So that's the idea, right? Increase in number of electron withdrawing groups, acid strength increases. Okay. The evidence for this, again, if you look at the pKa, this का 2.87 है, इसका 1.29 होता है और इसका 0.65 होता है. So this is more than 100 times acidic than with just one chlorine, with 3 chlorines. Okay. Again, the reason I'm writing these pKa's down is to drive home this point that the lower the pKa, the stronger the acid. Okay, because pKa वाले बहुत questions आते हैं इस chapter में. वो आपको pKa का data दे देता है and they like, you know, which is the stronger acid. All right. So obviously the idea here is that as you increase the number of electron withdrawing groups, if you're talking about identical electron withdrawing groups, if you increase the number of electron withdrawing groups, right, you increase the acid strength. Right, acid strength increases, which means that your Ka also increases and your pKa decreases. All right, next we're going to compare, let's say we have something like this, right? So I have this group over here. Again, I'm not showing the CH bonds, okay, versus this guy over here. Now, which of these is the stronger acid? First one or the second one? The first one, because the electron donating or electron withdrawing group is closer to the carboxyl group. Okay? So obviously the further away it gets, the lesser of an effect it has. Okay? Same with electron donating groups. This carbon has a lesser inductive effect than this carbon, and this chlorine has a stronger inductive effect than this chlorine. Okay? The further away the electron withdrawing or donating group, the lesser effect that it has. Okay? So again, this chlorine has a stronger electron withdrawing effect than the second one. The first one has a stronger effect. Okay, so the distance of the electron withdrawing group is another factor. Okay, I'm not writing down the full explanation, but the idea would be that the conjugate base for this guy, the conjugate base for 2-chloroethanoic acid is more stable than the conjugate base of 3-chloroethanoic acid because the chlorine atom is closer in 2-chloroethanoic acid, so hence it has a greater electron withdrawing effect and making it more stable, making this conjugate base more stable. Okay? So the distance of electron withdrawing group, as the distance increases, okay, we can say that the acid strength decreases, okay, and therefore the Ka also decreases and the pKa increases. All right. The last thing we're going to compare is if we have different electron withdrawing groups, okay. So जो आपने question किया था earlier, right? Here you have an iodine atom, let's say, versus a chlorine atom, right? Now, which of these would be a stronger acid? Chloroethanoic acid would be a stronger acid than iodoethanoic acid. The reason why is chlorine is more electronegative than iodine, so it has a stronger negative inductive effect, or it has a stronger electron withdrawing effect, okay? It has a stronger electron withdrawing effect than iodine, okay? So the last thing that affects acid strength is the identity of the electron withdrawing group, right, or the nature of the electron withdrawing group, right? As the electronegativity of the group increases, what happens to the acid strength? As the electronegativity increases, the acid strength also increases, okay? Because you have stronger withdrawal, so more stabilization of the conjugate base, okay? So therefore, we can say that Ka increases and pKa decreases, okay? So here, this would have a smaller pKa than this. Chloroethanoic acid has a smaller pKa than iodoethanoic